So that basically, in a nutshell, takes care of describing each source of the gravitational field, each black hole. And the point limit is just a world line with a bunch of curvature terms stuck on it. If you zoom out further than that, then you are dealing with a two-body bound state. So now we have two of these things in orbit around each other, bound gravitationally. I'm going to stick to the non-relativistic limit, where the velocity scales like that. The Schwarzschild radius divided by r, and it is assumed to be small, so this is an expansion parameter. The typical angular momentum in this problem, just because it's a parameter that's going to show up in the power counting. Well, the typical angular momentum is momentum times lever arm. In this case, mvr, we can write also as mv squared r divided by v. And so what this is equal to, so according to this formula, this is g Newton m over r, also known as m over m Planck squared r. So this thing is, using that formula, is m squared over m Planck squared divided by velocity. So angular momentum scales like the mass of the object divided by the Planck scale squared, and then it has 1 power of v downstairs. But the point is that this is huge. So we're using units in which h bar is 1, and L is huge because the masses of the objects that we have are like at least a few solar masses, and the Planck scale is a pretty modest mass scale, at least by macroscopic standards. So it's a classical problem, meaning that the action, whatever, the quantum of action, h bar, is much smaller than the actual angular momentum in the problem, which is the thing that the classical action will scale like L. And so the power counting is going to involve the velocity and this parameter L. So every diagram will scale like powers of L and V, and it will turn out, as I will explain, that quantum effects are down by powers of 1 over L, and we can certainly ignore those. One can compute them if one wants to, but for the actual, for the thing that's relevant to phenomenology, you can just drop it. So the action that's going to describe the system of 2-point particles is just the sum of two of those point particle Lagranges that I wrote down before. One for each object, one for each black hole, for example. So it starts out at empty tau, and then it has these curvature couplings, etc. And then the question is, how do we calculate the observables in this theory? And it turns out that they're conveniently summarized in a quantity that I'm going to write down as a path integral, but its meaning is purely in terms of Feynman diagrams that have a well-defined classical limit. The object, I'm going to call it, might as well be called the gravitational Wilson line, because it really is like a gravitational analog of a Wilson line. And what it is a path integral. The way that we're going to calculate it is we're going to write the gravitational field as flat space, eta mu nu, plus a fluctuation, h mu nu, canonically normalized, divided by m. We're going to do the path integral over the gravitational fluctuations with some boundary conditions. I'll say a few words about the boundary conditions in a second. And then it's the path integral e to the is. And the way I'm going to do this integral is I am going to hold the world lines of the particles fixed in arbitrary. So the action depends on those world lines. And I'm going to take the metric and I'm going to actually expand it not around flat space, but rather around some background, arbitrary background field. It's going to be weak. It's going to be a weak background field, and they call that field H bar. So this is some classical background. Well, everything's classical, but this is a fixed background, and this is a fluctuating field. And the idea is I'm going to do the path integral over the fluctuating field, holding the world lines fixed, and holding the background fixed, and of course the action also depends on the fluctuating field. So it's just a standard background field calculation with these world lines held fixed. And the way that you calculate this is that you can show that, well, at least at zeroth order it's just equal to 1. But if you keep going, it's equal to Feynman diagrams where you have fixed sources, and then you have graviton exchange between those sources. So the first term would look something like, well, here's the world line of black hole number 1, and here's black hole number 2, and the leading term is that they exchange a graviton between them. The way that you compute this is you use completely standard Feynman rules for gravity just by expanding around this background. So for example, the propagator that shows up here is just the graviton propagator. So the graviton propagator is something that has index pairs like that, and some momentum like that. It depends precisely on the gauge that you're in, but it's a massless propagator, so it goes like I over 2 squared. And then there's some tensor structure, which in the simplest gauge possible is just, so this is harmonic gauge, or the analog of Feynman gauge for gravity is something like this. 2 over d minus 2 mu 0. But it's not going to matter precisely what it is what we do. Anyway, the leading order diagram looks like that. And then there's more and more complicated diagrams. So at the next order, you might have 2 exchanges like that. You might have also, I guess I forgot to write it down, sorry. Before the exchange, there's also a term where the world line radiates one of these external fields that it couples to. There's also terms that look like that, where it radiates off of that. It radiates off of another end. It has nonlinear interactions somewhere in the middle, etc., etc., etc. So it just goes on forever. In principle, that's how you calculate this thing. Yeah.
What is the small parameter for this example?
I have not told you yet, right? At this point, there is no parameter. That's the whole point, to figure out how to make the parameter counting manifest. At the end of, I mean, what this is okay. I'll answer that.
Walter, so the intermediate particles that you have, which are just gravitons. So yeah. They're not propagator. They're just fixed.
Oh yeah. So that's an important point that I want to make. That the world lines are just there for decoration. So there's no propagator associated with that term. In particular, the way that in particular, for example, this diagram here. Really what it is a source, an insertion of a source, another insertion of a source, and a graviton between them. The world line is just to distinguish between particle 1 and particle 2, but there's no propagator associated with that. So another example, this diagram. This diagram is equal to where this source is, if you like, at least to leading order, is the energy momentum tensor for a particle. Okay, to leading order, I think that's what it is. That's the expansion, but this object, this Wilson line, actually exponentiates. One can show that. So what it really is just the exponential of the sum of, I guess, something that I call black hole irreducible diagrams. And what I mean by a black hole irreducible diagram is a diagram that remains connected if you remove these world lines. So this is a black hole irreducible diagram, so is this one, but this one is not. This one is actually this times this. So it's already accounted for in the leading order term in this one. It's just the product of two of those with a 1/2 factorial with a symmetry. So in principle, that covers everything. Let me explain to you. So this quantity, this Wilson line, can be interpreted as an action. It's some sort of effective action for the world lines and for the background field. So if you Taylor expand this order by order in the background field, it gives you information about the dynamics. For example, if you set the gravitational field to 0, the external field to 0, what this is, in the non-relativistic limit, for example, is just the two-body Lagrangian for the two particles. So it starts out like half mv² for each one, and then the one graviton exchange term gives you the Newton potential, and so on. So if you can calculate this object, you know this, Lagrangian, and then its variation just gives you the classical equations of motion. So that's the leading term in that Wilson line. And then after that, you can look at the linear term. So the order h bar term in the gravitational, in this Wilson line. So it's linear in the external field h bar, and let's call the expansion coefficient T mu nu. T mu nu is just, well, they're just defined diagrams with only one external graviton, right? That's what they are. But therefore, because of that, it can be interpreted as an effective energy momentum tensor for the entire system, for the two-body object plus the gravitational field stored inside it, all the energy and momentum stored in the gravitational field. It obeys a Ward identity, the Ward identity being that it is conserved in the usual way. It's not covariantly conserved. It's not the energy momentum tensor that appears in the Einstein equations. It's rather what's called a pseudo tensor, which encodes both gravitational and matter energy, and it's conserved in the usual way. It's the Ward identity associated with diffeomorphism invariance. If you know that object, then you can calculate the gravitational field very far away from the object. And this is where the choice of boundary conditions come in. So if I use boundary conditions where the propagators that I use are retarded propagators, more precisely, if I use what are called in boundary conditions in the path integral, then this quantity T mu nu gives you the waveform, or the gravitational field, very far away from the object. Go to infinity. And the way that it gives you that thing is just integral over the retarded propagator. So that's one way in which the choice of boundary conditions comes in. You could also, so this will give you the whole time dependence of the field at infinity. That's what that object gives you if you use causal boundary conditions, retarded boundary conditions. You could also use Feynman propagators, so usual I epsilon boundary conditions. In this case, the observables that you get, for example, this T mu nu of x, should be actually interpreted as some sort of time average observable. So instead of computing the field, the classical field at infinity, what this thing computes is rather amplitudes. Amplitudes for a graviton emission from this two-body bound state. So here is an example. So helicity plus or minus 2 gravitons with momentum k are related to that amplitude just by Fourier related to this T mu nu just by Fourier transforming. So what you do is you multiply by the polarization tensor of the graviton, T mu nu of x, and you get that, and that just gives you the amplitude for emitting a graviton. From the amplitude for emitting a graviton, if you sum over phase space, you get a decay rate. The decay rate depends on the observation time, which is going to infinity. And is equal to, well, phase space, so the final graviton phase space is the standard Lorentz invariant phase space. And then you multiply by the amplitude squared. So this is a graviton emission rate. It's a quantum object. You have to be able to resolve gravitons in order to measure it. But you can, even though you don't measure that, you can use it to...
Can I ask a question before you wrote that out? Just before you wrote that line out.
Yeah.
When you're connecting it to the stress energy tensor there,
Yeah.
that function right there.
Right.
Where does that come from?
Where does the T mu nu come from?
Yeah.
So what this is what's called a pseudo-tensor for the gravitational field. So if you look, for example, in Weinberg's textbook on classical GR, he writes the nonlinear Einstein equations as box. So he writes G is eta plus H.
Yeah.
And then he writes box of H is equal to the matter T mu nu plus all the nonlinear junk that you get from all the other terms of gravity. Okay? This object is exactly my guy here, it turns out. And you can sort of see that because the way that it relates to the field at infinity is just it involves the free propagator. In other words, the inverse of this box, right? So it's not a generally covariant object, but it obeys a conservation law. It just actually follows from the Einstein equations. So in field theory, the interpretation of this thing is as the one-point function. It's the linear thing in a background gravitational field. So that's what it is. Anyway, the point is that it generates all the observables that we're interested in. Because it gives you the rate, but once you have the rate, you can use it to calculate, for instance, the power flux at infinity, so the amount of power emitted in gravitational waves at infinity. It's some sort of time average, P dot mu, so the rate of change in energy and momentum. And it's just some integral over phase space weighted by this rate. And so once you multiply by the energy and momentum of the particles being emitted, it now becomes a classical object, free of infrared divergences of any kind, because, well, the h bars cancel anyway, because this thing goes, k goes like h bar times weight. You can also use this to calculate, for example, the angular momentum loss of the system. And when you do that, is you sum over helicities. So you can either lose energy to helicity plus 2 gravitons emitted along the direction n, or helicity minus 2 gravitons along direction n. So any classical observable follows from this quantity, this Wilson line. And in particular, all we really need for the classical problem are the first two terms in the expansion in powers of the background field. So that's what we're interested in calculating. Now the question is, how do we do this calculation efficiently? In other words, Dalian's question. How do we do this? How do we know when to stop? Because we're interested in an expansion in powers of velocity, but this thing doesn't seem to have any velocity apparent in it. And in particular, we don't know what the diagram scale was. So for example, here's the leading non-trivial correction to this. Well, just because I tell you in the non-relativistic limit, it starts out at order v squared. At least, it starts at order v squared. But it also has order v to the fourth terms and v to the sixth terms, etc., etc. So it's not the most useful way of doing things because we're interested in fixed order perturbation theory and velocity. We need a power counter. As another example, what about this diagram? This diagram comes in at some order, but just given the covariant Feynman rules that I alluded to so far, we have no idea how to assign some power of velocity to this. So we need a power counting. The reason why the diagrams don't scale homogeneously with powers of velocity is because we haven't really yet taken into account the fact that we are dealing with non-relativistic kinematics. So we need to put that in. In particular, when this graviton is being exchanged in this diagram, well, the fact that you have sources means that you're summing over all the momenta being exchanged. These are sources that are localized in X space, so they exchange all wavelengths of momenta. That's fine, but in the non-relativistic limit, in a sense, there's two preferred momentum regions, and we haven't isolated them. And in order to have correct power counting, it will be useful to isolate the momentum regions. This is, of course, inspired, so this idea came to us from existing effective field theories at the time, like heavy quark effective theory, or actually more appropriately, non-relativistic QED, QCD, which have similar momentum regions. There, the structure is more complicated because it's a non-abelian problem in a sense, but it's similar. So when you integrate over momenta in these diagrams, there's really two regions that matter. There's two regions that contribute in the two-body non-relativistic problem. One region of momentum we'll call the potential graviton region. These are momentum modes being exchanged that are nearly instantaneous. So the energy of these modes is approximately zero, but it's much less than the typical separation between these objects. And the typical momentum being exchanged is of order the orbital separation. So these potential modes, you can think of them, they're just the potentials. They're just the things that are there to bind the orbit, etc. They're instantaneous exchanges. And of course, the other momentum region that matters in this problem is the radiation region. So these potential modes are always off-shell. The radiation modes, though, tend to go on shell. These are modes that, because of the multipole expansion, have frequency of order velocity divided by the orbital frequency, orbital radius, sorry, and momentum of order orbital radius over r. So these guys are never on shell, these guys are on shell. And so the reason why we're not getting the right power counting is because we have modes in the theory that we shouldn't really keep. That we should integrate them out because they're off-shell modes. So the way that we actually do that is we split up the gravitational field into, well, we still have this background part, this G bar, we call it G bar mu nu of x. Then we have a long wavelength radiation mode that corresponds to these guys. We call it HR. And then we have the potential modes. And for the potential modes, because they are nearly instantaneous, and because of the difference in scaling between momentum and energy, it's useful to explicitly Fourier decompose the field into momentum modes and time. So we're working in, so for the potential mode, so these are going to be the radiation modes. These are going to be the potential modes. And the idea is that we want all derivatives acting on fields to scale the same way. So because in X space, this would have time derivatives that scale like different powers relative to the spatial derivatives, we're just going to explicitly include the momentum. We're explicitly going to Fourier transform. These momenta are the momenta being exchanged, the scale like powers of 1 over r. Therefore, any derivative acting on this field, well, it's only time derivatives really, but any derivative acting on this field scales like v over r, which is the long scale of the problem. Same with this, any derivative acting on this guy scales like v over r. That's the point of doing this decomposition in this way. So, so you decompose the gravitational field in this way. You have to gauge fix. You gauge fix in a way that preserves the background diffeomorphisms. This is called the background field method. It's familiar in gauge theories. You also have to multiple expand the couplings of, so I guess in order to derive this manifest power counting, this is the first step. And the other thing you have to do is multiple expand the couplings of the radiation field, HR mu nu of x. All that means is to just Taylor expand around a point somewhere inside of the source, like the origin, for example. Etc., etc. And then you just plug this into the action, and you find that when you do that, every term has a definite scaling in powers of velocity. So you can assign rules that tell you what every term in the action counts as, and then when you stick it into a Feynman diagram, you know exactly how many powers of velocity a Feynman diagram works or contains. So let's actually calculate that scaling. I can find my notes on it. So the way that we figure out the scaling rules is we just look at the propagators for each of these fields, for the radiation and for the potential. For the potential, well, the propagator for the potential mode is instantaneous. That's how it was defined. It's just a potential exchange between the sources. So the 2-point function, the free propagator for these two particles, for these fields, ignoring the tensor structure, scales like, well, it's instantaneous graviton that's being exchanged, so it has it's a 1 over r potential, or in Fourier space, it's 1 over q squared. And then there's a delta function that inserts spatial momentum. And finally, it's instantaneous, so it is proportional to a delta function in time. So we know how everything scales in this equation. This goes like, Q goes like 1 over R, so this is 1 over R to the minus 2. Q goes like 1 over R, so this is 1 over R to the minus 3. And X scales like R over V. It's the long wavelength scale in this problem. So this scales like V over R. So if I put everything together, the whole thing scales like R to the 4th V. And that tells me how, anytime this field appears, how it scales. what power counting I assign to it. So it tells me that every time you see it in the action, you assign this scale. You do a similar thing for the radiation. So the radiation is just a standard massless propagator. So in X space, you write it as a Fourier transform. 1 over q squared. So it goes like d4q over q squared. In other words, it goes like q squared. Q goes like v over r for radiation. It's the long wavelength scale. So this thing scales like v squared over r squared, and therefore the power counting you assign to the radiation mode is just sorry, q squared, so it goes like r squared over v squared. So this just goes like r over v. And now you can assign with this and the fact that derivatives go like v over r, and then coordinates go like r over v, you can assign powers of velocity to any term in the action. And so, for example, we can write down vertices that scale like definite powers. So, so just to do one example explicitly, we can talk about the couplings between the particle and the potential. So this is a vertex that looks like that. Let's say the 0, 0 component, which is what we're looking at. This is something that comes from the minimal m d tau term in the action. But m d tau, we can just take the non-relativistic limit, is approximately up to corrections that one actually worries about later. It's 1 plus h0, 0 over m Planck, which is approximately minus m over 2m Planck, dx0, h0, 0 plus stuff. And then we just plug in this expansion in terms of radiation modes and potential modes. And so this vertex is minus m over 2m Planck, Fourier transform dx naught of h0, 0 q. That's the coupling, and now we know how everything scales. It scales like m over n Planck times q cubed, so that's 1 over r cubed. And then h0, 0, which we just said was equal to r squared. Oh, and then there's the dx0. So there's that, and then dx0 scales like r over v. So this thing scales like m over m Planck. And then the powers of r all cancel, and the powers of v just gives you a 1 over root v downstairs. But remember, a few minutes ago, I worked out that m over m Planck scales like square root of L, the angular momentum, times the velocity. It's a huge scale. That's a huge number. And so what comes out of this is that this term here, dot, 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 0, 0, according to the power counting, just scales like square root of L. And therefore, this term in the action, in the Wilson line, just goes like square root of L squared. So the leading order term in the leading order diagram gets assigned power counting rule of L, much bigger than 1. If you were to look at diagrams that have loops in them, like this one, actual graviton loops, this thing would scale like 1 over L. So L is really the loop counting parameter, it turns out. It tells you what the classical limit is. And then there's some powers of V. I don't remember what they are. Anyway, that's how you power count any interaction. And then, of course, you're expanding the action and all sorts of powers of the different metrics. etc. And so there's going to be a bunch of terms, and all the different terms have different scaling. So for example, if you were to work out, as an exercise of the reader, I guess, the coupling between three potential modes, you would learn that it scales like b squared divided by the square root of L. So for example, this diagram here, where potentials are exchanged, but then they interact at the vertex, will go like, well, we just said that this one goes like root L, root L, root L, v squared over root L. So this whole thing scales like L v squared, and so on and so on. And then you just keep going. So here's one last example. Here's the coupling between radiation and potential. And that scales like v to the 5/2 divided by the square root of L. And the way you work out all these things is the same. And so now we have a power counting, and we can just grind out to whatever order we like. As we said, the terms with no external gravitons give you the potentials, and the terms with one external graviton tell you about the radiation emitted out to infinity. So let me talk about, let me sort of review some of the potential calculations that have been done.